Okay, so just kind of recap. Monday was introduction to the class. Tuesday was hopefully review of complex variables. There may have been some new content in there. And then today, and probably leading until Monday a little bit, is going to be, should all be review. Okay, so they may be, look a little different. They may be, posed in my flavor of teaching this material, as opposed to how you saw last semester, but it should be review. I hope these are comfortable concepts for you. We're going to go through things that you should have seen last semester. We're going to talk today mostly about linearization, the Laplace transform, and mostly then the frequency response. Okay, so of these three here, the most important one here is the Laplace transform. Okay, so if you were a little bit shaky on using the Laplace transform in 3260, it's not going to go away. We're going to use the Laplace transform on, not for like the first 6 weeks, but pretty much every single problem you see from week 6 to 14 is going to use the Laplace transform. I'm not exaggerating, actually. Okay. So there's going to be a very important concept in this class, and so you need to know how to use these tools in the frequency domain. Okay. All right, so jumping into this. First off, linearization. So in last semester, you should have seen some aspects of linearization, or maybe you've seen this in other classes before. Why do we linearize differential equations? What's the purpose of linearizing differential equations? Yes? Make them easier to work with, yes. Okay, exactly. No, that's exactly right. So it reduces accuracy. So your solution, if you use the linearized form of a nonlinear differential equation, is not correct. It's now an approximation, right? But it does make it easier to work with. So there are many nonlinear differential equations which me, nor you, nor anyone in the world knows how to solve. Okay, but every single linear ODE, there is actually a solution you can come up with. Okay, and so linearization is one of our fundamental tools in engineering to make problems tractable. Okay, so we can actually solve them and then design things as engineers, right? So the thing to keep in mind, it makes things easier, but you also need to keep in mind is that it does make your solution less accurate. Okay, so it is an approximation, and it's based off the Taylor series. Right? So a Taylor series is a way in which you can take some sort of function and repose it as a polynomial, and if you carry out that polynomial to infinite summation, it's perfect. Linearization, we're carrying out that polynomial to just the 0th term and the first term. Right? So we're cutting off a lot of those terms in the Taylor series solution for some sort of signal. So let's take a look at an example here. So nonlinear elements, the most simple nonlinear element you can think of is any spring, even though we may model this. The most standard force equation that we write for a spring is force is equal to the spring constant times the displacement of that spring, right? That you should have seen this a few times by now. So this is an approximation of how a spring behaves. It's not true. I think anyone who's kind of played with a spring before, they've seen this behavior before. So if you were to take a spring and maybe somewhere around L naught, it behaves like F is equal K times X in terms of when the length is L naught. So if you displace it maybe just a little bit, it behaves mostly like that. But if you displace it a lot, you get to a point where now these coils start to touch each other. And all of a sudden, the force that the spring gives is really large because you're trying to force metal into metal, right? The opposite is true. If you were to stretch this really far, you're going to get to a point where now, instead of being the spring that has compliance, it's now a straightened out wire, and that's going to be much stronger than a spring. Right? Okay. So you have a lot of behavior where it may behave in a linear fashion in this regime, and then once you get by some critical length, then it starts to really spike in terms of the force it provides. Okay. So simple element, definitely nonlinear. And so we're going to say, consider a forced mass spring damper with a nonlinear spring in example 3.1. And one model is people use for nonlinear forms of springs would be M x double dot to capture Mass times acceleration in terms of Newton's laws. You have damping at a mass spring damper, of course. And then we can have the spring force, which we're saying is composed of a linear term, so this is k1 times x, plus a nonlinear term. k3, x to the third, is equal to the force being applied. All right, so forced mass spring damper system. Okay, and so this says find a linearization of this example about the operating points that the acceleration and velocity all equal to 0, but the displacement is equal to some non-zero x bar. Okay, so what this is saying is we have a spring. It has a mass and it has damping associated with it, and we have displaced this some x bar. We want to know what is the linearization of this function about x bar. Okay, so we'll talk a lot about linearization and operating points when we get into some of the electromechanical machines, fluid machines. This is just kind of what should be a recap for a single variable linearization. So we'll talk a lot about those things, but the main thing is the operating point is usually up to you as the engineer to determine what the operating point. So your Taylor series approximation is always most accurate about your operating point. So it makes sense often to use an operating point that's close to how you intend to operate it. I hope that makes sense intuitively. So we're going to look at this Taylor series expansion. If you just reminder, the Taylor series expansion, if we have some sort of function, f of a, right? So this could be, whatever. It could be, say, cosine of a. That was written really sloppily. Right? That's a nonlinear function. Right? So if I want to approximate or write an infinite, so not approximate, I can write an infinite sum to describe cosine of a as a Taylor series expansion, right? And so just a reminder from what you would have seen in calculus class, we can say that f of a, the Taylor series expansion, is equal to f evaluated at a bar. So this is the operating point for a, so it would just be cosine of a bar, whatever a bar happens to be, plus the derivative of f with respect to a evaluated at a bar, and then a minus a bar, plus the next term, which is 1/2. Second derivative of f with respect to a. I ran myself out of room here. Okay, so note that this is now a nonlinear term. Right, so we'll talk about what we're going to do with that in a second, because we have a to the square. Right? And then on the next page, this goes on, infinite number of times. Oops. All the way up to the nth term as n goes to infinity. Okay, so in linearization, what we're going to do is we are going to truncate this Taylor series expansion at the first order. So this is 0th order, this is first order, and what we're going to do is we're going to get rid of this term and all of these terms to get a linear approximation for that element of our differential equation. Okay, any questions on that? Okay. All right, so in your homework problems, you have I guess the third problem, I think? Yeah, I think it's the third problem. You have one question that's a little bit of a stretch in terms of it may be something you haven't seen before. And I think the main thing is just try it out on your homework. I'm not going to actually ask that one on the test because it may take a little while. On the quiz, on Wednesday, it's a multivariate linearization. Okay, so you probably have not seen that before. But you may have seen multivariate Taylor series in your calculus class. Okay, when you have a function, instead of being f of a, say for instance you have a function xy. All right, so take a look back at your calculus notes from, or calculus book or calculus notes from freshman and sophomore year. There should be a multivariate Taylor series expansion. See if you can apply it to the problem in that one. It's not going to be asked in the quiz. It's more just for your personal knowledge. We will get to multivariate linearization though in this class, so that's why this is just like a little primer on that. Okay, so getting back to the problem at hand, we had so what we're going to do with linearization, we're going to just take Taylor series of the first order. We have, I'm going to argue we have 5 terms here. This will be term 1, term 2, 3, 4, 5. And I'm going to go through terms 1 and 4 only, because I just want to do 1 just to kind of show you what's going on there, and just say that a linear term, if you linearize it, becomes linear. It's still the same thing. It becomes itself. So if you linearize a linear term, it's itself. And then we'll get into the 4th term here, which is nonlinear. We'll talk about what that does. Okay, so if we look at the very first term here, the very first term is mx double dot. Right? And so if we were to say what our function is a function of x double dot. It's not a function of x. Right? So it's a function of x double dot. So we can say f1 is a function of x double dot. That's its argument. M is a constant if we assume that the mass is constant. And so if we were to look at what is, and this is mx double dot. And if we look at what is the Taylor series expansion for this term, it would be m x bar double dot, because this is going up to, I'll try and keep both these on the same screen, right? This is the first time, evaluate the function at its operating points. We're then going to take the derivative of that function with respect to the variable. And so if I look at what is the derivative of m with respect to x double dot, what is the derivative of this function with respect to x double dot? It's just m, right? So it's going to be plus m. And then we have x double dot minus x double dot bar. Sorry, those merged. There's an auto function that merges things sometimes. Let me rewrite those. Okay. Now if I were to go to the next term, say I didn't want to do linearization, I want to go to the next term, this would be the second derivative about respect to x double dot. If I were to do that, first derivative gives me just m, second derivative gives me 0, right? So anything above first order just is all zeros. So those don't exist. Okay, so if I look then at my operating points, I had mx double dot. The operating point for acceleration was 0. Operating point for acceleration is 0, and then we get back mx double dot. So pretty boring, right? So this is just showing that if you, just really quick, if you linearize a linear term, you get a linear term. Nothing exciting. So on your test, etc., see a linear term, you don't have to, and it says linearize this whole differential equation. You can pretty much just skip all your linear terms and just write them down. Okay. Next term that is a little more interesting is what happens with, actually let's do 3 and 4. I think that may be helpful to see. We'll go to 3. It's linear, but it's going to help cross out or cancel out with some things. So a little more quickly, f3 of x. Let's do it all in one. So k1x plus k3 x3. All right, so I evaluate this. Now this is going to be an approximation. It's not going to equal because we have a nonlinear term in here. So f3 of x is approximately equal to this function evaluate its operating point. Okay, plus the function with the derivative with respect to x. So in terms of respect to x, I get k1 plus 3 k3 x squared. Now keep in mind I have to evaluate this at the operating point. So this is x bar. And then x minus x bar. Okay. Any questions why I did that? And then, let's see, so those are your major terms. Oftentimes in linearization, we institute a change in coordinates. So we have change in coordinates, x is equal to x hat plus x bar. And I'm going to actually rewrite this, but I want to make sure it's clear that what's a function of time and what's not a function of time. So we have x of t is equal to x hat of t plus x bar. So x bar is a constant. That's not a function of time. X is a function of time, and x hat is a function of time. And so what we're saying here is these are functions of time. All right, so we have some sort of function x. I'm just making something up right now. This is our function x. We said we have an operating point, x bar. And what I'm doing is just by changing coordinates or just a translation, I am defining a new variable, which is x hat. Try and draw this as accurately as possible. That's x hat. Okay. Any questions on that idea? Okay, so putting this all together, I get the equation m x hat double dots. Now keep in mind, if I take a look at the first derivative of this function, I get the first derivative of x hat, first derivative of x is equal to the first derivative of x hat, because this is a constant. And same with the second derivative. So these are interchangeable. Okay, then plus then my Taylor series expansion carried out to first order. Okay, changing coordinates, right? So x minus x bar is equal to x hat. And then this all equals f bar plus f hat. And you'll see why I'm doing this in a second. I ran myself out of space here, but I'll find some room. Let's see. I think there's a way to add a page in here. At least the advertisements trying to convince me to buy this program is saying I can add a page. All right, I'm not going to have you sit through things I should have done offline and by myself. So let's then wrap this all up. The thing to then keep in mind is if we were to evaluate this differential equation, going back to our differential equation, if I were to evaluate this differential equation at its operating point, so everywhere I see an x, I put in an x bar, I would have gotten k1x bar plus k3 x bar to the third equals f bar. So this is the static equilibrium for my mass spring damper system, right? So if this mass spring damper system is at rest, I know the, say, the force on it, I know also the position, I can solve for that. Okay, so what this does is allow us to cancel out terms. So we know that k1 x bar plus k3 x bar to the third is equal to f bar. So I can go down to my differential equation that's been linearized. I see on the left-hand side k1 x bar plus k3 x bar to the third. And on the right-hand side, I see f bar, right? So this all cancels, right? So now I have my linearized differential equation. 1 second, and I'll get to this. Just to note, this now becomes a linear mass spring damper. Mx double dot plus Cx dots is equal to this constant times x. Yes?
So we can just derive the k1 x bar plus k3 x bar k3 bar.
Where I scrolled up and did that? Yeah, so this is going back to the differential equation that's coming from Newton's laws here. So what I'm looking at is what is the steady state equation here? And so by steady state, I'm turning the second derivative and the first derivative equal to 0. So when this thing is at rest, right? So it has no velocity, no acceleration. Yes?
Like, I think I'm missing something, but would it not be okay just to linearize the x to the third term? Isn't k to the x already linear? So hope we treated it as one function. Could we not just linearize?
Yeah, so I think this is always the struggle when I teach this is that the first time you see linearization or the second or third time, it's kind of this big mystery, and then you get the pattern, and then students will just like skip everything, and then they can get pretty good at just writing down what the solution is. So I guess you're kind of asking along those lines, like why couldn't I have just said, all right, this term's linear, I know it's going to cancel out with the f bar. Why bother? Is that what you're asking, or maybe I'm off base?
Well, yeah, I'm not exactly sure of the f bar.
Okay.
But I just from system dynamics before this, we would normally just like x to the third is the only nonlinear term.
Yeah.
So that would be the only thing we would like be concerned with.
Yeah. No, I completely agree, and that's why I didn't do the expansion for the cx dot either. That's linear. So the main thing is that if you have a linear term, it's going to be linear, and it's also going to cancel out when you apply the static equilibrium as well. So depends on how you learned it, or maybe you get really good at it, you see, all right, linear, I'm just going to cancel it. If you want to skip that step, that's fine, right? Because but this is showing the long form of why, when I take a linearized version of K1x, why they actually end up, the K1x bar cancels out. Yes?
Do we just define f bar to be that value, or where did that come from?
F bar is the solution at equilibrium, at rest. All right, so there will be some practice on linearization in homework 1, and also one that's a little bit of a stretch, but like I said, it will not be on the quiz. I'm going to skip section 3.2. This is given in full form in the notes, but this should be, we're going to go through electrical elements and fluid elements quite a bit in this class. And so I think it's probably best we'll go through all these analogies of how we can write mechanical systems or electrical systems using exactly the same equations of motion. We'll go through that a lot. I'm not going to bother going through that right now, but basically any system is, mass spring dampers are equivalent mathematically to inductor, capacitor, resistor systems. And so you have the analogy of the mass is equal to the inductor, the damper in a mechanical system is equal to the resistor. So these are lossy elements. These are kinetic energy storage elements. And then the spring and the capacitor are both potential energy storage elements. And we'll talk about that a lot. We'll also look at fluidic systems as well. That's this little chart right here. The main thing I wanted to get to in today's lecture is the Laplace transform. Because I said that there's pretty much week 6 through the end, every problem is going to involve the Laplace transform. So it's very important that you understand the Laplace transform. Okay. So the Laplace transform of a function f of t, so this assumes that you have some sort of function given already. Either it's something you're solving for, or you actually have an explicit form of this function somewhere. Right? And so if we know this function, and if we can do this integral transform, we can find the Laplace transform of that function. So the Laplace transform is defined by f of s. So just a note, reminder, we use uppercase letters when we're talking about Laplace transforms, and we usually have the argument s here. Now, as the class goes on, and you're going to see this pattern where I take the Laplace transform as almost the first or second step of every problem we see, I'm just going to drop the s because it's just going to get really tedious. But for now, we'll leave it in. So f of s is equal to the integral from 0 to the left-hand side to infinity of f of t e to the negative st dt. Whereas reminder, S is a complex number. Okay, so that is the integral form of the Laplace transform, just for definition's sake. That's probably the last time you'll see me write this in this class. Okay, so we're going to almost immediately skip towards known solutions of the Laplace transform. So by known solutions of the Laplace transform, is that coming up soon? Yeah, I'm just going to zoom down to there. Okay, not as close to, as I thought it was in the notes. Okay, there we go. There's what I want to see. Laplace transform table, right? So these tables are on Wikipedia. They're on essentially every single system dynamics controls book you'll ever find. They're all basically the same. Here's my version of it, which is borrowed out of a textbook that we don't use here at Ohio State. But they're all basically the same. It's a mapping between functions in the time domain, right? So left-hand side, time domain, and the Laplace transform. Right? So we'll go through some really simple ones, namely the direct delta function and the step function in a second. The one thing I want to point out to you, though, is that the Laplace transform is only valid for time greater than or equal to 0. Okay, so that may seem limiting, but it's worth noting because sometimes you can have tricky problems where you can no longer apply the Laplace transform. In this class, we're looking at controlled systems. We're saying that, all right, we have a system that's at rest. We're going to turn it on. That's time 0, and everything's going to proceed from there, and it's not a problem. But just to note, it's only valid for time greater than or equal to 0. All right, so I would either make sure your textbook you're using on test, etc., has this, or print this out. And also note, any test given in this class is going to have a Laplace transform table at the last page or second to last page. It's going to be somewhere handy. Okay, so Laplace transform, this is then the kind of just a note or an aside saying that Laplace transform, oftentimes you'll say, if you take Laplace transform, it means we are transitioning into the frequency domain, right? Where you were in the time domain before, arguments in time. Now we're going to the frequency domain, which we talk about arguments in either S or S being equal, it's a complex number, to some sort of function that has a real part and an imaginary part associated with it. And so this has kind of elements of frequency associated with it, right? So here's our definition of the Laplace transform. If I, step back. Step back. This is our definition of the Laplace transform, and this has the e to the negative st term here. If I now substitute any generic complex number, S is equal to sigma plus I omega, that's equal to this. And then if I expand this out using the Euler's equation, I have a cosine omega t. This is a harmonic function, and I have an I sine omega t as well. Right? So I've transformed the function into having just purely in time domain to having elements of frequency to it. All right, that's pretty much all I want to say about that, but basically this is why we call it the frequency domain. There's an inverse Laplace transform. We'll never use this in this class. We'll be using the tables. Okay, but some things we will use are the definition of poles. So what are the poles of a Laplace transform? How do we determine what the poles of a Laplace transform are? Yes? Yeah, so the roots of the denominator of the Laplace transform, right? Okay, so the definition in 3.3, the values of S such that, can't write, the denominator of f of s is equal to 0. All right. Analogously, we have a definition for the zeros. And so this is a very similar definition, but we're talking about the numerator instead. So instead of the values of s such the denominator of fs equal to 0, it's the same thing to start out, but that the numerator So as a quick little aside, say for instance, you were to see on a test, take the Laplace transform of e to the negative at. I take the Laplace transform of that. That's one thing I forgot to mention. If I ever use this script L, that means we're taking a Laplace transform of that function. And this is equal to 1 over s plus a. You can find this in a table. So if we look at what is the pole of this Laplace transform, the pole is negative a, right? That's the value of s such the denominator is equal to 0. This, in particular, this function, this Laplace transform does not have a 0, right? There's no value of s such the numerator is equal to 0. Okay, so just going through some simple, this is all in the notes. I'm not going to go through this. This is an example of how you would take the Laplace transform of sine omega t. Some other ones that are of interest is the first off, the step function. Okay, so we'll be using the step function a lot in this class. Okay, so step function u of t is defined by u of t is equal to 0 for time less than 0 and 1 for time greater than or equal to 0. So what this means is that the step function has this form. So for time less than 0, it's 0. For time greater or equal to 0, it's equal to 1. Okay, so we will use the step function oftentimes to denote that something has been turned on. Okay, so something being turned on means that some level has gone from 0 to some nominal value. So by nominal means we can scale the step function, right? So that you can think of that as a light switch is a really good example. So like for instance, we have basically in this room we have relays controlling all the lights. So for instance, if I switch to house full, right, when I did that action, it's activating an electromechanical relay somewhere in this building. I don't know where it's at, but it's allowing current that was currently stopped at that switch or relay to now go from current being 0 going through that relay to now whatever the current value is, right? So that would be equivalent to whatever that current value is times the step function, right? So that'd be one example. Yeah, voltage and, the voltage drop across the switch is different, but then the voltage across the light would now be going from 0 to some non-zero number. Right? Okay, so we're going to use it for turning systems on. For some reason, there we go. Seems dimmer in the room than it was just a second ago. Okay, it's supposed to be bright projector. I don't know. Those relays are broken, I guess. Also, the things that we're going to be looking at is, say, robotic systems. So step function can represent a command for the robotic system to go from, say, position of 0 to position of A, or say 45 degrees. So say I have a robotic system, it has a revolute joint in it, and I want this robotic system arm to go from so for you guys, right, this is 0 for you, it's good because my arm doesn't bend this way. So this is 0, and then say we wanted to go from, a command to go from 0 to 45 degrees. That would be a command saying 45 times the step function for the reference function, right? And so that's how we're going to instruct robotic systems how to move. Would be one way in which we can do it. Right? Other examples, you've probably in your house, you've heard the air conditioning cycling on and off, right? So just to zoom in here. So most air conditioners are pretty simple. Same thing with your oven in your house. You have your ovens either on full bore or it's off, right, in terms of the heating elements. So if you're setting it to, say, 450 degrees Fahrenheit, it sets up what's called a hysteresis loop, where if the temperature gets below a certain amount, it turns on. If it gets above a certain amount, it turns off. Same thing with the air conditioning system in your house, is that you have some sort of threshold for the low temperature, right? So once the temperature measured by the system gets below that low temperature, it turns your air conditioner on. I'm doing the opposite here. Sorry about that. Air conditioner, that cools things, right? All right, so if your temperature gets too high, the compressor turns on. That decreases the temperature in your house. If it gets too low, in terms of it gets too cold for you, it turns the air conditioner off, and then the temperature increases, right? So these would all be ons, offs. These would be step functions in terms of how we can represent them. Okay, any questions about the general concept of the step function? Okay, direct delta function. 6. Okay, so direct delta function is a little bit more abstract than the step function. Okay, so limit as epsilon goes to 0 of this function called delta epsilon, where delta epsilon is equal to 1 over t epsilon for absolute value of t less than or equal to epsilon, and is equal to 0 for t greater than epsilon. So I'm reporting this how most undergraduate textbooks report it. It's actually a Gaussian function, it's a little more complex. Yes? 2 epsilon. Okay, so this is the simplified of the direct delta function. It's a little bit more intuitive when it's in this form. But what we're saying here is that the direct delta function is equal to 1 over 2 epsilon in terms of height for the range of t being between epsilon and negative epsilon. So what's the area of the direct delta function? Always 1, right? So if we look at the area, right? 2 epsilon wide, 1 over 2 epsilon high, right? So as I take the limit, as epsilon goes to 0, this function gets to be very, very narrow, or infinitesimally wide and infinitely tall. Okay, so direct delta function can often be thought of as any function or any input to your system that has a lot of energy or a lot of force delivered over a very short period of time. Okay, so some examples of that. Okay, so I'll probably zoom in here. Okay, so some examples of that. This is a trace of the pressure in a cylinder in an internal combustion engine. So you probably can't read the units on the x-axis here, but these are degrees of basically degrees of the full cycle. So you have, when you have ignition, you have an incredible spike in the pressure in here, and it's over a fairly short period of time. So this is not perfectly a direct delta function, but acts somewhat like it, right? So we could potentially model something like this. with the direct delta function as approximation. On the right here, these are tools that you can purchase. What the purpose of these is looking at structural dynamics. So if you want to try and understand, experimentally understand how a system vibrates, one way you can do that is you can buy this instrumented hammer and hit it with a hammer, and then that's going to excite the system. It's going to cause a bunch of vibrations in the system. And so what you're doing in an experimental point of view is you are putting a direct delta impulse function into it as a force. And so this instrumented hammer, you can buy this. You can put accelerometers on your structure. You then whack it with this hammer. This has a little force sensor in it, so it's actually going to understand how hard you hit it because it has a force sensor. And you can look at from a more of a theoretical point of view, if I put a direct delta into it, what was the response of the system? Other examples, we have this video here. Oops. Okay, of course we have to watch ads. Okay. For some reason, this HDMI cable is not carrying my sound. Okay, so what this is looking at is a baseball hitting right here. All right, so this is just what is this? I forget what the show's called. But basically, it's looking at a baseball hitting a baseball bat, right? So if a baseball is delivering a lot of force on that bat, you can see if anyone who's held a baseball realize that these are pretty firm, right? So it's delivering a lot of force, so much that it actually can almost crush this baseball over a very, very brief period of time, right? So one way in which we could look at this is a lot of force being delivered to that baseball bat over a very brief period of time in terms of the interaction time between a baseball and a baseball bat is very small, right? So just kind of an aside of maybe some intuitive ways in which you can think about these functions. Okay, so some properties of the Laplace transform. Probably the most important thing in terms of properties of the Laplace transform that we'll use in this class is how to take derivatives. Okay. So one of the things that's so great about the Laplace transform is it takes derivatives. If you were to solve the ODE regularly, that's calculus. If you take the derivative with the Laplace transform, it's actually algebra. Okay, so that makes our life pretty easy in some respects. And what I mean by that is if I say, if I have some sort of function, if I have some sort of function f of t, and the Laplace transform of that f of t is equal to this f of s, and I now want to know what is the Laplace transform of the derivative of f of t with respect to time. This has the property that it's equal to s times f of s minus f of the function itself evaluated at 0, or times equal to 0. Okay, so we've taken calculus and now turned it into algebra. We just now multiply by s, and then we add then its initial condition. Not always in this class, but most often we're looking at systems at rest or starting at rest. So pretty often the initial conditions will be equal to 0. Higher order derivatives. Say, for instance, L d2f dt is equal to dt squared is equal to s squared f of s minus f naught minus f primed 0. So what is the velocity of that function? Right? And then we can keep on doing this on and on and on. So I want to take the 100th derivative of some sort of function and know the Laplace transform. It's actually pretty easy to do. Okay, but you're just multiplying by s. Integration, how do you take the integral of a function? Divide by s, right? Okay, so pretty easy. Final value theorem. Time domain. Okay, so final value theorem. So the final value theorem, we're going to be looking at basically what is the long-term solution of any type of function. So oftentimes we're going to look at if we tell a system to go from basically one output to the next output, we want to know, does it actually ever get there, right? So we want to know, as time gets really, really large, did it go to the position we wanted it to go to or not? And so we're often going to use the final value theorem for that. So the main caveat to this, and this is always like every control professor's best trick problem, is that you need to have all the poles of S of F have to be in the left half plane, or left half of the complex plane. So if any pole in the right half plane, this doesn't work. Okay. So if all the poles of S, F of S are in the left half plane, then we have the property that the limit as time goes to infinity of f of t is equal to the limit as s goes to 0 of s f of s. So in the last 5 minutes or so, yeah, we should actually get through this a little bit more in the last 5 minutes. So it is a quick problem. So say for instance we have, and this problem is just to kind of show a point, but say for instance you're given some sort of Laplace transform. It is 50,000 over s times s squared plus 0.2s plus 10,000. If we were to do the inverse Laplace transform of that function, what would be f of t as time goes to 0? Right? So if we actually do the inverse Laplace transform of that, that's going to take a pretty considerable amount of work and probably take you like 20 minutes on a test to do this problem, because you have 3 poles, it'd be a decent amount of time, right? But the final value theorem allows us to get this pretty quickly. So given this relationship here, just quickly, we'll take like 3 minutes or so. What is the limit as time goes to infinity of f of t? So just kind of work on your own for about 3 minutes, and then we'll revisit this, and we'll also take a look at what is the solution for f of t and kind of show some of the crazy paths it can take to get there. Yes. Yes. Yeah. Sorry? No, yeah, it's not. Yeah, so it has to be, so sorry, they're in the left half plane. So the imaginary axis is not in the left half plane. So doesn't work. But it's all the poles of S times f of S. So it's, can you look at that? It's S times f of S. So if you look at that, S cancels. Yeah. Do you have a question?
Yeah, like, so on a test, I don't, oh, never mind.
Sure.
Like, would you give us numbers like this on a test? Like,
Yeah.
then we would put them into the,
Yeah, so this is this. Yeah, so we're using if we use the final value theorem. If you're to actually solve the inverse Laplace transform, this would take you a long time.
right. Like, how simplified do you want our numbers to be?
Okay.
Like,
Okay.
like, could I just leave everything in?
Today we're going to go through the most complicated version of this problem.
Okay.
So the answer is 5.
Right.
Okay.
Right, yeah.
Okay. So if we look at this, so if we were to do the inverse Laplace transform for this, it would take us much longer than 3 minutes, right? Because you have 3 poles, you'd have to then expand this out to 3 different terms. But if we look at using the final value theorem, this would be just then limit s goes to 0 of s f of s is equal to 50,000. Sorry, I forgot the s in the numerator times over s squared plus 0.2s plus 10,000. Right? S's cancel, these go away because we evaluated 0, and we get 5. Right? So it's a very easy way to jump. If the problem asks you what is the solution at time goes to infinity, or what is the solution at a very many seconds from now, it's a very easy way to get to that solution using the final value theorem. So it gets rid of a lot of the mess. So if you're actually, I'm not going to put it in MATLAB right now because I want to get to another more important point. But here's the actual solution here. In time, these transients are so crazy that my computer can't even resolve them. It oscillates like mad. And then it finally settles out after 50 seconds to 5. Okay? So if you ever want to know, if you don't care what happened in between, you just want to know what happened at a very, very long time period, the final value theorem is a very effective tool for solving that. The very last thing I wanted to go through is this correspondence between a Laplace transform and time domain solution. I am going to be gone on Monday because of a personal reason, but I will, when I get back, Instructor Lake is going to be teaching the class on Monday. When I get back, I'll revisit this again because I think it's very important. If there's anything that, if there's any content that you learned in 3260 that you must know and carry on to 3360 is this idea of the correspondence between the poles of a Laplace transform and this time domain solution. We'll probably can only get through like one of these right now. But this map is going to be very, very helpful because like I said in the first class, we're going to stop worrying about what is the exact solution of the functions so much as we're going to start looking at what are behaviors? And we're going to look at the poles to try to understand behaviors. So earlier in this class, I talked about if we had a pole at negative a, that's distance a from the imaginary axis, it had a time domain solution that looked like a decreasing exponential, right? So this is a function in time that we'll say decays, right? So decreasing exponential. If a gets larger, the solution here is e to the negative at, right? If the pole gets larger, so now I have some pole way out here, farther away from the real axis, the solution converges faster, right? What happens in case if I have a pole in the right half plane? So I see people with their pencils going like this, right? It explodes. Right? So these are exploding exponentials. This is the function looks like this. Okay, so if we want, just kind of foreshadowing this class, if we want controlled systems to ultimately converge to say we want to say, all right, here's where we want our system to go. We ultimately want that system to go there. Do you think we want converging or diverging exponentials? Converging, right? So you do not want to say go to position 45 degrees and then your robot goes off to infinity, right? It's obvious, but that's a really bad feature. So what we're going to be doing throughout this class, we'll always be looking at trying to design systems such that the poles are in the left half plane. I'll get into on, Instructor Lake will go through this on Monday, and then I'll hit it again on Wednesday next week. Filling out this map more. This is only real poles so far. We'll talk about complex poles on Monday and Wednesday. All right. Have a nice weekend.